The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
I can start by reviewing what we talked in the last lecture. We introduced thermoelectric effects, including feedback effects. When we have a temperature difference, a voltage is generated. That's the phenomenon, right? And then we give a microscopic picture of the what happens. This is really the diffusion of charge. On one side of the path, the charge diffuses to the other side. And the Peltier effect is when we have a junction that's made of two different materials. We pass current through it. You will have either cooling or heating effect. Depends on the direction of the current flow. And this is because the charge itself also carries heat. So when the charge flows from one material to another material, if there more heat flows out, then the junction cools down. And if there more heat flows in, the junction heats up. And then you reverse the current direction, you can see that effect is reversed. And the Thomson effect is when we have a uniform conductor or semiconductor, when we have a temperature difference imposed on it and flow of current through, then along the material there is uniform cooling, there is a distributed cooling or heating that happens along the material. And this is because really at each section of the material, because of temperature difference, the charge, the electron, carry different amount of heat. So that's the Thomson effect. And then we did analysis, simple analysis of a device. We have a real device, we pass current through it. There is the thermoelectric effect, but there are also undesirable side effects. Those side effects is one, there's jar heating, and two, there is reverse heat flow, conduction, and this degrades the device performance. And if we do the device analysis and find out the efficiency or the coefficient performance, we found that those depends on eventually the material property, which we call the figure of merit ZT. And of course, those are heat engines, so the pre-factor is a Carnot factor times something that's less than 1. And this less than 1 is dependent on the material property. And ZT, we want it to be large as possible. And then we discuss applications. I mentioned that like at this stage, the materials is not competitive to replace the main refrigerators or main power generator like an internal combustion engine. So there are two directions to go. One, if you're an engineer, think about really using those. There you have to look at the system and the innovation, where it makes sense from both the efficiency and particularly cost commercial product point of view. And the other direction is go to improve the materials. So what we'll be talking in the today's lecture and next lecture is understanding what really determines the microscopic aspects of the materials and what are the directions we should go to improve the materials. What are the ideas? So let me again start with this figure of merit ZT. I said that when you do thermoelectrics, you say I work on thermoelectrics, often people ask you, what's your ZT? Right? That shows you know something about it. And it has three parameters: the electrical conductivity, the feedback coefficient, and the thermal conductivity. And the thermal conductivity, the heat conduction in the material, or consists of two parts. One is atomic vibration, a lattice in the material. The atoms in the material vibrate and conduct heat. And the other is when charge itself, right? It carries heat, so it also conducts heat. So here we decompose this K into phonon and the electron. So those are the, when you think about ZT, you look at those parameters: electric conductivity, Seebeck coefficient, and the phonon contribution to thermal conductivity, electron contribution to thermal conductivity. And what I want to do next is to dive into more details. So what are the microscopic pictures determine those properties? And what are the physical, together with some mathematical formulation for those properties? So today I hope we will cover those topics. We will first review some basic concepts in solid states, and then using the simplest picture, that's the same picture I talked in the first lecture, how we use the three-step. I derive Fourier law, right? It's really particle going from left and minus particle going from left to right, minus from right to left. So with that imbalance, you will see we can come up with expressions for the electric conductivity, Seebeck, thermal conductivity, all this. And then I will do a leap of phase. I'm not going to do detailed derivation. From this, we can go to more formal transport theory and have the more rigorous expressions for the transport coefficients. So let me start. Like I said, this is a review, but I know for most of you it's new. Because if you, for example, from mechanical engineering, you have not seen this. So don't worry about it. You just let's follow through. Some you take, say those are the results from physics. Others, I hope the picture is simple enough for you to appreciate those pictures. So let's start with the basic concepts. First, in terms of the atomic vibration. Because atomic vibration in the solid carries heat, right? So now I think about the bonding between atoms. You can think of this either solid or even just a hydrogen molecule. The bonding between the two hydrogen atoms in the molecule, when they are far apart, they are attractive. And then when they are too close, they repel each other because the electrons start to overlap, and the quantum mechanics will say the basic principle is the exclusion principle. It doesn't allow the electron to take the same orbital. So we have a typical potential curve in the far separation between the atoms. It's attractive, and when they're close, it's repulsive. And the atoms stays in the equilibrium position here. So when we have many atoms, they will have constraints on both sides. So they have a most stable position. That's where the energy is the minimum, right? Now, because this curve, the energy is the minimum. If you look at the mathematics, when I have a curve minimum or maximum, the first derivative is 0. So when I look at the expansion, I can expand this potential into the minimum point plus the first derivative 0, then I go to second derivative. So you can go to higher order, but for the understanding here, we just go to second order, and then the force between the atoms is just the derivative of the potential, right? So F equals the potential derivative, so I get a force equals the spring constant between the so now we can treat these two atoms, the vibration, as a spring. So it's a mass and spring system. And for mass spring system, we all know the simplest picture is a mass spring, right? and there is a lateral frequency for this vibration. The vibration frequency is the spring constant and divided by the mass of the atom. This is very relevant when you think about what the material you want to choose for thermoelectrics. And typically, the larger is the spring constant between the atoms, right? You look at this, the higher is the frequency, the more vibrational energy, the more the bonding of the atom is stronger, there is a larger spring constant. And this will lead to high thermal conductivity. And diamond, for example, has the highest thermal conductivity among the materials, and that's because the bonding between carbon in diamond is very strong, and the carbon atom is very light. Okay, so that's just it has implications for this, even though it's very simple. And this is what they learn in classical mechanics, dynamics, right? The lateral frequency of vibration. And if you go to quantum mechanics, what it tells you is just a small addition. You know what I'm saying? The frequency is still the same, nu is still the same, but what it tells you is that energy cannot be any value. We all know quantum mechanics, the basic sense the energy is quantized, right? So if your oscillation is at this frequency, in classical mechanics, the oscillation amplitude, the velocity can be any value. And in quantum mechanics, we say the energy must be integer of this h nu. Okay, so that's the new thing coming from quantum mechanics. So it must be multiples of the h nu, and so this h nu you can think this as a basic energy quanta, and that's in solid is called a phonon. And this one half is also related to the so-called uncertainty principle in quantum mechanics. It's also called the 0-point energy. So if you recall before I talked about the photon, right? When we look through electromagnetic wave, and this atomic vibration is analogous to the electromagnetic wave. So those are all waves. We'll extend this more to waves in the next step. So that's where the link coming from. Photon for electromagnetic wave, and the phonon for lattice vibration. And that's the basic energy quanta of vibration. Okay, so this is we're talking about the individual oscillator. And now I look at the atomic chain, right? So when I think about solid, the most simple picture is crystals. Crystals are periodical arrangement of atoms. So now I start with one dimension of atomic chain, and the distance between the atoms is the lattice constant A. So we have n atoms. So the length of this chain is Na. Now again, you recall in the electromagnetic wave, the last lecture, I derived the Planck's black-body radiation law. I said that when we consider cavity in the length direction, I have standing wave. Now I'm going to make the same argument. If I clamp the two ends of this atomic chain, do not move, right? Again, take a rubber band as an example, right? You fix this end, you oscillate it, you see the waves, different waves, right? And the violin is another example, right? So the length gave me, those are the wave, the constraint. The wave has to be multiples of lambda, which is the wavelength over 2. So I have the length must be multiple lambda over 2. It could be any integer. And then the wave vector. Again, I'm talking about, because it's a wave, so the inverse of the wavelength is the wave vector is 2 pi over lambda. That's the definition. And fundamentally is like the Fourier transform, right? If you're an electrical engineer, the time signal, a sine omega t signal, the period is t, and frequency is omega, the relation is omega equals 2 pi over t. The same, this is a spatially periodic vibration, so the wave vector and wavelength relation is 2 pi over lambda. So that's a Fourier transform. And so this is the standing wave picture. When I climb the two ends of the lattice Chen, I have those are the allowable wave vectors. And I went this pretty fast in the last time I talked about electromagnetic wave, but I did say the standing wave, when I read the mathematics, you go to check. When I wrote mathematics, I say I can do the summation of two traveling waves. One goes from left to right, the other is go from right to left. So here k is 2 pi over lambda, those are the values. So now I do the traveling wave. So rather than climb the two ends, I say, okay, I don't have that constraint. The waves can go both positive direction, negative direction. Okay? So in this case, the wave vector is pi over from minus pi over a to plus pi over a. And two traveling waves will make a standing wave. So if you have the same wavelengths there. And but also, if you compare what I wrote before, okay, I didn't put any limit, right? So this way, the wave vector can have any value. On the other hand, when I think about very large wave vector, what it means in a crystal, because the two atoms, the smallest distance is here. Now, if you have a wavelength shorter than that, it doesn't mean much. Okay, so that's why I say my wavelength is limited to here. If you look at this, this is a 2a. The one atomic distance is a. So this is the minimum you can have in terms of wavelengths. So those are the region of my wave vector going from negative pi over a to plus pi over a. Now you think about the frequency, right? When I talk about the one atom vibrating, the frequency is k over m, square root of k over m. Now when I have the whole lattice, right, different wave vector, so each wavelength corresponding to one mode of this vibration. And think about if my whole atomic chain is one wave, right? One wave pure, one pure. The frequency is higher or lower or same as my individual k over m square root. Anybody is making a guess?
If all atoms move in phase,
Yes.
I'd say it's the same as the natural frequency.
Well, let's suppose, again, let me take this as right. Now, all the atoms move in just one pure. All the moves. And the next is one pure. Okay? And more pure. So in terms of frequency, do they change or they don't? You probably can go back and do an experiment and put some beads over, say, rubber band, and then you will find out, right, the relation between the frequency and the wavelength. In this case, is changing, right? When all the atoms move in unison, let's say only one pure, it looks like the whole atoms, all the atoms in the chain is moving same time, right? So it's slower. The frequency is smaller. So that's in the long wavelengths, this is a wave vector. Long wavelengths, frequency is smaller. And when you go to larger wavelengths, and at the end, it's close, coming back to here, you can see here is K over M square root. So come back to individual atom attached to spring, high frequency limit. Okay? So this is the relation between the wave vector and the frequency is, again, the dispersion. Remember, for photon, for electromagnetic wave, omega equals ck. That's a linear dispersion. And here, the real one we have is approximately half a sine. This is like a sine function. And often we do a linear approximation, take the slope. So the speed of sound is that's the slope is for the longitudinal wave, that's the speed of sound. So in solid, okay, you log one end, propagate to the other end. That's the speed of sound. And that's this slope here. Okay? And a very high frequency, when you go to look at the put the mass of atom, you can see this frequency can go as high as terahertz or tens of terahertz. So very high frequency. Of course, the acoustic wave that we can hear is only a few hundred hertz. Okay, so this is a simple one monatomic atomic Chen. And now if I extend this a little bit, suppose my Chen has two different atoms, right? Gallium arsenide as a crystal, right? One atom is gallium, the other atom is arsenide. And I have, so in this case, this is one period. From between the two atoms, the same atom, that's one period. Of course, one simple picture is the other atom is moving in unison with this atom, so it forms the same phase in the two sets of sub-atoms, that is. And this, in this case, the dispersion, the relation between the wavelength, wave vector, and frequency is similar to what we drew before. And in the other case, we could have this set of atom moving up, the other set of atom moving down. So it's a much harder stretching, right? They are very close. You are forcing them in terms of a different phase there. It's much harder stretching in the higher frequency, stiffer. So in this case, we have two types. We might have two atoms. One is the acoustic branch. That's the bottom part. That's this picture here, roughly. The other is the outer phase. That's the optical branch. Okay. So that's the atomic vibration in one dimension. And of course, a crystal is not just one dimension. A solid is not just one dimension. It's three dimensions, right? So any direction you look, it looks like you got a one-dimensional periodical arrangement. It's just that spacing between the atoms could be different. So how we express it, right? So here, we'll go back to what I said before, Fourier transform. And the periodic signal, if the period is t, we see the frequency is 2 pi over t, right? And in terms of wave, in one dimension, wavelength is lambda, and the Fourier transform is 2 pi lambda. But in three dimension, each direction has a lambda, right? If I look at a crystal, a cube, take a simple cube, put them periodically arranged, you look at diagonal direction, the period is square root of 3 times the lattice constant A. So that's your periodicity. You look at the, say, different plane, crystal plane, you have different periodicity. So what I do is I transform this periodicity in space. Okay, let's say I take a crystal, as say here is a say face center structure, face center cube. Every face on the surface there is also an atom, and I do Fourier transform of this space in 3 dimensions. That's what it looks like. Now it looks a little bit ugly, okay? But I can say each crystallographic direction, here is a k direction, right? And the shortest distance, L, this point, is the longest real space, right? Because k is 2 pi over lambda. So if I think about this from center to this point, the shortest, I know for a cube, that's a 1, 1, 1 direction. It's the inverse of the atomic space. So this is a way that the physicists like to use the reciprocal space. I joke with them. I say, you guys don't live in the real world. Right? They like to express things in the reciprocal space. So now let's look at it simpler in terms of mathematics, expression things, right? You go to electrical engineers, they like to do signal analysis in frequency. They don't do time signal, right? Time signal you have to plot at the time. You do power spectral analysis, you got to use frequency. It's much simpler mathematical language. Okay, so now you get to the real world. Because that, before it looks very simple, now you can start to look at the string. You know, for most mechanical engineer, you look at this, you'll get the, what is that? You know, say, it's really to look at the different crystallographic direction, the vibration frequency. And if you look at this, all silicon, gallium arsenide, all face center cubic, as I drew before, different crystal has different those different directions, different reciprocal, the shape of this basic unit cell in reciprocal space. So I look at the gamma direction. That's a 1, 0, say 0, 0. So this is diagonal from this to this, diagonal direction. So if I look at that direction, what's the vibrational situation, spectrum? So if I have the lattice wave propagating in the diagonal direction, so that's from gamma to L, right? And this is those are the optical phonon, those are the acoustic phonons. Acoustic phonons start from 0 here, optical is from the top of the acoustic. And why I have different branches? I have different branches because the vibration, the sound wave you're receiving is longitudinal. Air is longitudinal wave only. But in solid, you can have longitudinal as well as transverse. You can experience, you can sustain the shear. So I have longitudinal wave, transverse wave. And really transverse, if you look at the electromagnetic wave, I said there are 2 polarizations, right? See, acoustic wave transverse also 2. But in highly symmetric direction, like from gamma to L in this case, it's a symmetric. So the 2 directions, this direction and this direction, the same wave vector, they have same frequency. So they become degenerate, just plot 1. But in some other directions, not highly symmetric, you can see clearly 3 polarizations. Longitudinal, 1 longitudinal, 2 transverse. So acoustic branches, optical branches. That's the extension from 1D to 3D. Yes.
What is the spacing between the different wave vectors?
Different wave vector, the spacing. Those are experiments. The data is a comparing experiment.
Frequency should be in like hours or frequency.
Frequency is in like hertz.
Frequency is if it's omega. So this is another thing that very often people get really confused because depends on who likes to plot on what, right? And sometimes here is K, omega, and sometimes you'll see this one is not plotted omega in terms of the frequency. This is centimeter inverse. Well, that's not a frequency unit, right? So what they mean? And in this case, if you want to look at the first frequency is 2 pi mu, angular frequency. Right, you have to say what exactly is that, whether plot the angular frequency or frequency. And mu is, if they plot this wave vector inverse, they plotted 1 over lambda. Okay? So you have to convert the frequency equals C divided by lambda. So the people have different habits. Yes?
Is this the speed of sound or speed of light?
Huh?
Speed of sound or speed of light?
This is the speed of sound. Oh, I'm sorry. Speed of light.
Okay.
Yeah, not speed of sound. When they do this kind of expression, they always go the speed of light, vacuum. Speed of sound is different for different materials. Okay, so you're asking what are the wave vector numbers? So this is where, right, the number of waves when I go from here to here. This is called from pi over a minus pi over a to plus pi over a. That's called the first free-flowing zone. And the number of wave vectors k equals the number of atoms you have. Okay. So this point, so from here to here, the number is n. That's actually important when I later. This number is all important when you do counting. Once you go to microscopic picture, you do the counting.
In silicon dispersion relation, we have a mode that seemingly corresponds to the optical mode in gallium arsenide. Then what will be the mode will look like for the silicon at the top then?
Oh, they mean optical modes. Well, it turns out silicon, it's one lattice point. How many atoms? Okay, and silicon is in one lattice point. You have 2 atoms. So there is another atom. Say that 1 quarter, 1 quarter, 1 quarter. If you think this is 1, right? There's another. This is a lattice. This is a point, a lattice point. So there's another atom at the 1 quarter, 1 quarter, 1 quarter. It's not 2. It's a FCC, but there's two atoms. If there are 2 atoms, then say in lattice point, if there are 2 atoms, then there are 3 acoustic branch. 3 acoustic branch, and then there are another so 2 atoms, right? N minus 1, so times 3. So there are 3 optical branch. If you have 3 atoms, you have 3 acoustic branch, then you have 6 optical branch, right? So the total is 3 times n. That's n is at every lattice point how many atoms you have.
What's the direction of the 2 transverse wave?
Roughly is perpendicular, but when you actually do it, you have to solve the dynamic matrix. You have to solve the matrix to find out the exact direction of the vibration. The eigenvectors. You can always decompose, right? But there's an eigenvector that you should go to solve the equation of motion. You can solve Newtonian equation of motion to get those eigenvectors. Okay. That's all about crystal vibration. And now, let's say the electrons, right? I started with the crystal vibration by hydrogen molecule. I have the two atoms and the separation sprints, mass sprints. And when I talk about electron, let's also start with hydrogen. This time I'm starting with the hydrogen atom, right? And the hydrogen atom, again, you go quantum mechanics. This is the energy levels of hydrogen atom, electrons in this case. I'm talking. And the electron, the energy level, I didn't even write it down. You can say I wrote, so E of the electron is depends on the N, is a minus 13.6 electron volts N squared. Okay? So what is the one? So let me say the 1 electron volt is when electron move in one charge of electron move in 1 volt, 1 voltage, electric field 1 voltage, and that's the energy of the electron. And this is equals to 1.6 10 to the minus 19 joule. So that's the energy of the electrons in the hydrogen atom. And it's electrons moving in 3 dimensions, right? And so when I solve the Schrodinger equation, I'll find the wave function. Again, this is going quantum mechanics. We're not going to do any quantum. I'm just introducing the basic concept. And it turns out because we have a 3-dimension r theta phi in 3-dimensional space, so there is 3 quantum numbers n, l, m. Okay, those are all results of quantum mechanics, except that in S. You have to go to even relativistic quantum mechanics. And those n, you can see now all integers. Those are the quantum number. N is allowed with 1 to 3, all those integers. L must be less than n, m must be less than l. Those are all mathematics, coming from the mathematics. But what it really means is, I wrote down that I forgot to write the energy. Energy is minus 13.6 electron volts divided by n squared. So energy doesn't depend on L and n. Depends only on n. Right? So when n equals 1, I have L has to, you look at it, L has to be 0, M has to be 0. And the S could be plus and minus 1/2. So there are 2 quantum states. So here I have 2 quantum states. So you look at the periodic table, that's why you have hydrogen, helium, field. Helium is stable. 2, field. And the next quantum level, you go to n equals 2, is pretty far away from first level. Right? So you look at the periodic table again, you feel this is the 1 quantum state. 1 quantum state can only have 1 electron, maximum. Right? That's when I count the spin as a different state. So hydrogen, helium, lithium. Lithium, okay, it's still 2s now. So you go to continue look at the periodic table, you fill in here each energy level is 2n. Once you go to n equals 2, the total number of electron you can have up to fill all the orbital. The quantum state is n equals 2 is what? 8, right? 8. Okay. So that's the hydrogen atom, and this is a basic model for the periodic table. You look at the periodic table, you can use this and pretty much interpreted a lot of those first 30 atoms or so. Now, I'm going to, again, starting from here, I'm going into atomic chain, because I want to understand electrons in solid, right? So atomic chain, thinking about hydrogen as a simple example, but the hydrogen, of course, is a gas. But I'm thinking about solid, and so electrons, they are waves in quantum mechanics. It's both waves and particular characteristics, right? So waves, each electron has those wave function I plotted before. This is the wave function. The quantum mechanics will give you this function. And now they are waves. So let's plot n equals 1 approximately. And they spread out, not just confined to one electron. And now this is the next atom, n equals 1. They start to overlap with each other. Right? What happens? And these two electrons from the two atoms want to have the same states, because once they start overlapping, the state of the two atoms are the identical states, and the basic quantum mechanics doesn't allow it. Okay? So the state will start to adjust a little bit and form bands. So now n equals 1. This is original n equals 2, 3, 4. I think now they start forming bands. So there are, if you have n atoms again in the chain, from between here and here, I have n points. And each point now they start to you can see here, side different. And those same allowable wave vector, now electron is a wave extended through the whole lattice. This is a one quantum mechanical state. So the waves can have different wave vectors, different pure, same as we argued for the lattice. Right? So that's a basic quantum mechanics dictate the energy has to split a little bit, forming now a band. It's quasi-continuous. We plot the continuous because of that K, there are many K points. But they still, between here to here, there are n points. And the n is your number of atoms in the chain. Okay, this is very interesting because even this simple picture, I said the hydrogen picture tells you the periodic table. What this picture tells you whether you have an insulator or conductor. Let's think about, if I take a hydrogen as a simple extreme, each hydrogen has one electron, right? So when the electron field go to the energy, the lowest energy level fills first. They are lazy. Okay? That's the first. The thermodynamics tells you, right? Everybody wants to go to minimum energy states. So if I have n atoms, I have between here and here n point. Each point has a spin. The spin is not reflected in this curve. Okay? So each point has two states, two spin. S equals plus minus half. So now I start to feel the bottom electron, if I have hydrogen, and feel there are really two n quantum states. I have only n electron. Where it goes? It feels about half, right? So the electron maximum number, energy will be, this will be where somewhere in between. between the band. Okay. So this is where depends on hydrogen, I said the field here, depends on how many electrons you can fill to within the band. And if it's at 0 temperature, 0 Kelvin, this point where the topmost, just think about the water filled bucket, right? The topmost energy level is called the Fermi level. And so if it's a non-zero temperature, those electrons cannot move. They need a lot of energy to move, right? Because there's no quantum state in this here quantum mechanics. There's no state allow this energy to move to. When they move, they change state. The state has to be adjacent, allowable in the solid. So only electrons in this region are movable. And in metal, because the next state just close to this point is very close. The energy difference is very close, right? So the thermal energy is large enough to allow them to go to the next state. So only when your electron fail to level their empty state in the band, it's a conductor. It's metal. That's metal. Okay. And what happens if my number of electrons fail to here? Then it needs a lot of energy, right? Depends on the difference of the energy here and here. If this difference is very large, you got an insulator. Electron cannot move. So this from the topmost of the electron to the next empty state, that's the band gap. Okay? And if this band gap is very large, that's an insulator. How large is large? A few electron volts. And this is because at room temperature, we said that in the first class, the energy is about kBT. K is Boltzmann constant times temperature, thermal energy. And that's about 26 milli-electron volts. Right? And so if this one is a few electron volts, much larger than kBT. So very, very few chance the electron can come over here due to thermal. And it's insulator. But if this gap is not large, glass, for example, is insulator. Right? And the gap is a few of about 4 to 5 electron volts. Now silicon, that gap is about 1.12 electron volts by room temperature. So silicon become a semiconductor because this gap is not very large. And if you cool silicon to 0 Kelvin, it should be an insulator. Because there's not enough thermal energy to keep the electron from here to here. But at room temperature, the thermal energy kBT, because of the thermal energy, some electrons are kicked from here to here. And if they are kicked from here to here, what's left behind are some empty states, right? Now those electrons, those other electrons feel happy now. There are some states they can move. And these other electrons that picked up is also happy because there are also empty states they can move. Right? So the motion of those electrons, it's much easier. So you can think this, the thing that's really moving is the electron moving because they're empty states. But it's much easier to think than as a positive charge. So don't think of those as electrons, just think of those empty states as holes. There's no hole, okay, no positive charge. It's electron that's moving. But we just think this as holes, positive charge, and those are electrons. And you can even put so that's the intrinsic silicon I said, right? But you could even put the impurities into silicon, into semiconductors, to add more electron or add more holes. So when I add, for example, if I put the phosphor in silicon, phosphor has 5 charge. Silicon is 4 in the outer shell. So there's one extra compared to silicon. So that extra, because it's very close, the energy level of phosphor is very close to the here, so that electron can easily be excited to this region. So it's an N-type semiconductor. And on the other hand, if I put the boron into silicon, the outer has 3, right? So the boron energy level is somewhere here, close to the bottom of this band here. This is the valence band, this is the conduction band. So the energy level is here. Those electrons are much happier to go here, so left behind the poles. So boron become an acceptor. They trap that electron, and they create the holes in those bands, empty state in this band, that the electron are happy to move. So that's how you do doping in semiconductor. You create the energy state. Sometimes even impurity, even weakened state, could create those additional states. Depends on in semiconductor, in silicon, we do artificial doping. When we do thermoelectric materials, a weakened state, the missing atom could create those kind of situations. So the doping in material, in thermoelectrics, doping is very important. Of course, this is true for all semiconductor devices. Okay. Any questions here? Now, let's move on. Look at the real material now. Right? Let me say that's a one-dimensional picture. And I look at, again, 3 dimensions. Go to the virtual reciprocal space. And 111 is the gamma to L point direction 111. I only draw half of it because it's symmetric. Positive wave vector, negative wave vector is symmetric. I draw half to save space. Okay? So this is the gamma to X, the 100 direction. And it turns out the silicon, the maximum point where this electron is filled to as a valence band, and the minimum point, that's the conduction band, they do not agree in terms of the wave vector. So this is an indirect semiconductor. And gallium arsenide, on the other hand, is a direct semiconductor. Okay, there's a big difference in these 2 materials, direct and indirect. Microelectronics industry is established on silicon, but the lasers, semiconductor lasers, nobody can use silicon to make semiconductor lasers. People are making progress. It's much more difficult to make a laser out of silicon. It's a direct gap semiconductor is much easier. The reason is that in a gallium arsenide device, microelectronic device, you inject the electron here, you inject hole. That's by device design. You put a current, you actually inject into the material, and then electron fall off to the bottom of the so from recombine from between here and here, give off a photon. Right? It's much easier to do that in direct gap because there's say null wave vector mismatch, and here it's very difficult for electron recombine with the hole. Well, you say that's good for solar cells, right? Solar cell you don't want recombination. Really, you want to get the charge. But there are various points. This one solar cell is not good. It does not absorb well. can create when a photon comes in, right? A photon, the wave vector, the wavelength is about 1 micron, right? The wavelength of photon, half micron. Let's think about the visible light, half micron, right? And the wave vector of photon is 2 pi over lambda, 2 pi over half micron. And here is 2 pi over A. A is Lagrange constant, a few angstrom, right? So this is a few angstrom. If it's 2 pi over half micron, that's exactly almost right at the center, right? The wave vector of photon, very small. Wave vector h over lambda is the momentum. Momentum of photon is very small. So in gallium arsenide, the photon comes in, you go from here to, if the energy is large enough, you can lift the electron from here to here, get absorbed. But in silicon, because the indirect semiconductor, the photon momentum is here, you cannot lift the electron from here to here. It doesn't have enough momentum, it has enough energy. If one can solve that problem, through some method, you solve a huge problem. Okay? So this is a really, even in the microscopic world, it's an energy conservation and momentum conservation. You learn either in continuum or in discrete. That's always true. Okay? So silicon don't absorb well, gallium arsenide absorb well. If you look at the gallium arsenide solar cell, people use the thin film. They absorb well. Silicon, it's very hard to use the thin film because they don't absorb. You get it, so your compromises might make thicker for that chance to happen. Yes, but that's exactly how it absorbs packets. You need a phonon, right? Phonon has that wave vector. Phonon doesn't have enough energy. That the omega is too small. So phonon plus a photon give you the wave vector. Photon give you the energy, can lift from here to here. You've got the 3 particles work together, right? Think about your coordination at MIT. Get the 3 professors together. Much less chance. That's the probability issue. Right? You all have that experience. Okay. Now we're going to do a little bit more. That's a basic idea of the energy levels, vibrational energy level, and the electronic energy level in solids. And I'm going to do a little bit more. And I approximate. First, I think about the free electron. The kinetic energy, 1/2 mv squared. Right? And the mv squared, quantum mechanics, first m times v is momentum, so p squared 2m. That's still just a relation from p is mv. And in quantum mechanics, p is hk. So, I forgot the h squared, sorry. Should be h squared k squared over 2m. So that's a free electron. Okay? And for electron in the solid, I'm going to do a similar treatment. Because this here is maximum, here is minimum. Right? Again, the first order derivative is 0, unless this is very sharp. There are some cases it's not, the derivative is not continuous. So the band is not a parabolic, it's not a continuous curvature there. But say most of the case, this maximum, minimum, the first derivative is 0, so I have second order maintained. Right? Mathematics, Taylor expansion. So here, if I, for example, take it E minus EC, of course I put a K, I didn't put a K, this is not 0, so I should put KX minus K0 squared. Here I put the center at the center. So this is the semi-general, not the most general form of doing the mathematics, right? And here it looks very similar to free electron. This is just a second order derivative of the curvature. Now if I treat that just as a mass, equivalent mass, I call the effective mass, then it's a free electron. I can then do the rest of my work as a free electron. So mathematical simplification. Here are the effective mass of the electron in the crystal. If I take that effective mass, I write this pretty much like a free electron. So I'm going to do free electron most of the time, except replacing the mass. So this is again my dispersion relation, right? Before I said dispersion relation between frequency and wave vector. And now if you think about energy related to frequency h nu. So frequency, wave vector. Except that for electron, people don't talk about frequency. People like to talk about energy. Those relations between wave vector, frequency, or wave vector, and energy are dispersion relations.
So the effective mass is different for every direction?
It could be different for every direction. It could be, in some cases, it could be isotropic. Okay, actually, next one, let me show you. Now, if we take the energy as constant, I draw this, right? If you look at this, if this is okay, what's the constant energy surface looking like? In 3D, if these are the same, it's a sphere. They are different, they are ellipsoid, right? Elliptical. So, this is what's in gallium arsenide. This is a silicon electron. Right? Ellipsoid. So in this case, we say, okay, there you got 6 carrier pockets, different directions. Okay? And this is just a review. I showed this before. Now we know what is phonon, what is electron. And Fermi-Dirac distribution is for electron. Bose-Einstein distribution for phonon and photon. Most of the time, this mu is 0 because phonon and photon are not real particles. It's another way. They're not real. They can disappear. Right? Electron also disappear, but most of the time cannot disappear. Electron can not disappear. Electron is a real particle. When you go from conduction band to valence band, recombine. It's just that the electron still is there. Okay. Okay. Now I'm going to do math. I'm going to do more detailed company. I say, okay, I dope a semiconductor. Yes.
Sorry, is there any concept of like mass conservation or effective mass conservation?
Mass conservation for good question. I don't think that we can talk about mass conservation for under the effective mass picture. I'm sure this is only from, I think that most is from transport point of view. Electron, of course, the true mass is still the 9.1 to the minus 31. But in the solid, when you look at the transport, I treat that as a free electron. Then due to the field, the drag of the background lattice, so now they feel either heavier or lighter than the free electron mass, which is 9.1 to the minus 31 kilograms. Yes?
When people do the band structure calculation for electrons, do they assume independent electron approximation? If they include electron,
I think they should include the electron. This is for example, you do density function theory calculation. They will include the other electron effect. and you don't do a free, just an independent electron. You have electron influence other electrons even in the same atom. Right. Okay. So now I'm going to do a spherical. I'm not going to do parabolic elliptical bands. I'm going to do a spherical band. M is the same in all directions. Okay. So that's like really like a free electron, except that this mass could be different. Like I said, it's good for gallium arsenide, right? Let me suppose I want to find out if I dope the material, how many electrons I have in this conduction band. Okay. And I'm going to do counting. So this is a strategy that I use, and it's I used before same for photon. I did that photon in a cavity. I count how many photons in the cavity, right? So now if you remember, each quantum mechanical state can have one electron, and the state, what's the average number of electrons, is given by Fermi-Dirac, maximum one electron, right? We said this is the average given at a certain temperature, chemical potential, average number of electrons in one quantum state. Now I just need to see how many quantum states I have, right? One quantum state, this is the average number of electrons. So I just need to really, all those counting looking very complicated. It's just a counting quantum states. And before when I do electromagnetic wave, I was counting electromagnetic modes, same way, right? So all that counting how many modes. The modes is essentially a state, right? So I'm counting. So in the x, so it's 3D, kx, ky, kz. And kx, I have nx number, n atoms in the x direction. Ky, ny number. Kz, nz number. Okay? And the factor of 2 is because I have a spin. Electron spin 1/2 positive minus negative. Electromagnetic wave is a factor of 2. If I want to do phonon, maybe it's a factor of 3, right? Because the non-trivial transfers, if they are all the same. Okay? And so this is the number of quantum states, and this is at each quantum state, what's the average number of electrons. You can think that for phonon or for photon, it's all the same way. Right?
It's counting the real vector, it's counting the number.
Well,
What's the number minus nz over 2?
This is a yes. It's the counting the number, but say then I do the integration conversion. Okay, here.
I think it's counting the real vector.
Okay, here is I'm counting n. These are the discrete states, right? And this is a standing wave picture, so everything is positive. And when I do traveling wave 2 directions, I said that these are equivalent. Okay? So that's why I go from negative n top to positive n top. It's just an equivalent. Okay? Why I count the numbers? Because my next step is to convert the number into integration. Because counting states, right? And it's better to do integral states rather than fractional numbers. This is the number states. That's where I convert this. If I think about wave vector k is a continuous function, and between two states, that delta k is 2 pi over L. So this is converting this integer summation into the summation into integration. Right? I did that same thing when I do electromagnetic modes. So in the x direction, this is the length, but the next two adjacent k n is 2 pi over Lx. So this is the number convert into here, correspond here. So here I have the integration kx, ky, kz. Those are all mathematics converting and say the conversion and the counting. And the reason I want to do this now is I have the integration dkx, dky, dkz. And 2 pi now I have is 8 pi cubic. Lx, L by Lz is the volume, factor 2. And now the F, I'm going to just ignore the 1 plus 1. That's a Boltzmann approximation to the Fermi-Dirac distribution. Okay, so I plug in this F already here. So that's my number of electrons in this region, in the conduction band. Okay. I encounter this classical problem. My integration is over wave vector. My function is over energy. Right? Same thing in electromagnetic wave. My function, my integration is over kx, ky, kz. My function is over energy. And I have to choose either energy or wave vector as my variable to do this integration. I already have the relation between E and K. That's my problem here. E and K. Right? So I'm going to do that conversion. In this case, it's much easier for me to convert dkx, dky, dkz into E, because you can say that's a Cartesian coordinate. I can convert it into spherical coordinate. And so I'm doing this conversion. Now I do per unit volume lumbar density, and I do that dkx, dky, dkz. In spherical coordinate, k is the magnitude, right? So it's 4 pi k squared dk. Right? So that's from Cartesian to spherical function and pairing it. Now I replace, because I know the k squared is 2me minus ECH squared, right? That's the expression. This is a h squared times k squared. That k is my radius, like r, right? So I replace this k squared. K squared equals 2 pi e minus c over h squared. dk becomes this d, and everything is in energy now. It's the trick you do all the time in counting the numbers in crystal. You convert the states, number of states summation into integration. You choose your either integration variable either in energy or wave vector. And if I group everything all together, this is my F, and this one I call it the density of states. Okay. It's used, it's mathematics. Density of states is nothing. The physics-wise is it don't have much physics. It's just a mathematical way of saying doing converting my summation into integration. So this is the number of quantum states per unit volume because I normalize the volume, and per energy interval because here is d. Right? That's a physical interpretation of my derivation. And in fact, you go to look at this one, you can do the integration analytically. That's why I use the Boltzmann distribution. If I put a Fermi-Dirac, if I put say 1 over this, not this plus 1, I can do this integration, okay? So the reason I use the Boltzmann distribution is that I can do this integration, and this integration gives me, here is a kBt, and here is E minus E mu kBt exponential. So how I determine the chemical potential mu, if you give me the number of dopant, so I put the phosphorus in the semiconductor per unit volume. I put how much, I know that. And if I assume each phosphor donated 1 electron, assumption, right? And there are most rigorous statistical way to see how many electrons are activated. But because phosphor energy is so close to silicon, so you can roughly approximate this. Every atom that you put in there donated 1 electron. So with that, I know the left-hand side. I can do the inversion. This is where my chemical potential is. So chemical potential is determined by the number of carriers you put there. And then you will see in thermoelectrics you have to optimize this carrier density to get the maximum performance. Okay. So let me summarize this. Right? This way of doing the do the level counting, you can always start with that summation I said. But at the end, most time you will end up with this density of states. It's just that you derive density of state every time. Once you become comfortable, you can say, okay, this is I can write it directly. The number of electrons per quantum state. This is the number of quantum states per unit volume per energy interval times dE. That's the number of quantum states there. And that gives me the number of electrons near energy E. And I integrate over all possible energy states. That should give me the number of charge. Right? So once you gone through this a few times, you can just start from those. And I wrote down for Boltzmann statistics, under Boltzmann distribution, I can do this integration, and that's what we have. And what it means is, if I gave a number of dopant to the like phosphor, I can see where my potential is, chemical potential is from here. Given n, I inverse, I know E minus EC. And the Boltzmann statistics is only valid when this mu is far below EC. Once the mu gets into here, you have to use the Fermi-Dirac statistics. That's a degenerate semiconductor. This is the only approximation. But here is general. You can always do that math to inverse to get a given number, you can get the chemical potential. And the density of states is a mathematical concept, but it's very convenient. And really, it's a number of quantum states per energy interval the wave. And in the parabolic band, it's a parabola. It's a square root relation. Density of state equals square root. And of course, below EC, this is where EC is at the bottom here. There's no states in this region, in the forbidden band gap. So that's a typical bulk material density of states. And then when you fill, it turns out that most of the time it's only a small region because of this here is a KT. So electrons are mostly in this region when you dope the material. Once the NE becomes very large, that exponential factor very small, much larger than KT. This is very small. Okay, so that's what we went through, and I thought that I was doing much faster. We'll do the next time. This is actually just right on my project original syllabus. Any questions here? No. If you're a mechanical engineer, again, I'm sure this is the normal mechanic. Talk about this, and I don't expect that you'll completely master it, but I think what you'll get is, say, oh, I know the periodic table, I know the metal and dielectric difference, right? And I know the atomic vibration in the crystal is quantized, and the basic unit of that quantization is the phonon. So now you know electron, you know phonon, and then the thermal conductivity, remember, comes from electron and phonon. And in thermoelectrics, the S squared comes from electrons. So you have to really get this basic picture before we talk about the next step. Any other questions? Okay.